Good day. My name is Jamnda. I'm one of the engineering students at the University of South Africa. Today I'll be presenting my report that speaks to automatic power factor corrector. Efficient use of electrical power is crucial in today's energy-driven world. The management of electrical power factor is essential in electrical energy, assessing power quality and ensuring financial and environmental benefits. Power factor is a dimensionless quantity that represents the phase connection between voltage and current. A low power factor can lead to an increased energy expenditure, decreased system efficiency, equipment overloading, voltage drops, reduced motor efficiency, power quality issues, compliance challenges, and extra capital investments. Monitoring and controlling power factor is crucial for a more effective and economical electrical system. The study aims to evaluate the necessity of automatic power factor correction solutions to address the rising reactive power consumption, energy expenses, system efficiency, and potentially equipment damage caused by inefficient electrical systems. It seeks to find the method to increase power factor and reduce operational costs without compromising infrastructure stability. The task at hand is to design an automatic power factor corrector device that can improve power factor, reduce reactive power, enhance equipment performance, monitor and adjust the power factor of electrical systems automatically. The device should be capable of detecting and correcting the power factor in real time, ensuring that it remains as close to unity as possible. The device should be able to work with a wide range of electrical loads and should be cost effective, energy efficient, and easily to install and to maintain. The user requirements of the device. The device should meet the following minimum specification. The device should be able to measure and display the power factor of the total load. The device should provide automatic power factor correction to a range of 0.9 to 0.99. The nominal voltage of the load should be 230 volts AC. Reliability is essential. The efficiency solutions are frequent of interest to users in order to obtain optimal energy savings. Automatic power factor systems should be constructed to reduce energy losses and run capacitor optimal. Literature review. Power factor is a measure of an electrical system efficiency comparing real power, which is measured in watts, to apparent power, which is measured in volts amperes. It is typically expressed as percentage or decimal, denoted by symbol PF. Real power is energy used to drive motors or heat sources in electrical circuits, while apparent power is the total power given to the system. Reactive power oscillates between sources and loads without performing useful work. Power factor correction is crucial for minimizing losses in electrical systems for several reasons. Firstly, it improves energy efficiency by reducing the amount of reactive power wasted. Secondly, it reduces energy consumption by reducing reactive power generation and transmission across the electrical distribution system. Thirdly, it maintains voltage stability, preventing voltage drops that can impair the functionality of sensitive equipment. Historical perspective. Power factor correction techniques have evolved from manual to automated system due to advancements in electrical system knowledge and technology. Early manual method involved constant monitoring and modification of electrical load or switch capacitors. Automatic capacitor control devices reduced manual intervention and improved efficiency. Static VAR compensation correct reactive power dynamically using power electronics and semiconductors. Active power factor correction systems improve power factor correction by monitoring voltage stability and harmonic distortion, making real-time adjustments using microcontrollers and digital control algorithms. These techniques enhance power distribution network stability and energy efficiency. Power triangle. Power factor is calculated by using this formula: the real power over the total power. Type of power factor correctors. Automatic power factor correction systems aim to enhance reactive power compensation and power factor in electrical systems. They can be categorized into analog, digital, hybrid systems. Analog systems use analog control circuitry for power factor monitoring and correction through capacitor switching using analog sensors to detect voltage and currents. Digital systems use microcontrollers-based technology and digital control techniques, providing more accurate, real-time monitoring and adaptability to shifting load condition. They optimize capacitor performance through complex control algorithms, improving energy efficiency and power factor correction. Hybrid systems combine analog and digital control techniques, using analog sensors for basic measurements and digital controls for more precise control. They also provide digital control with additional analog reductance for greater dependency. These systems are suitable for application where a combination of digital and analog capabilities is desired or where a fully digital solution is too expensive. Compensation techniques. Capacitor compensation is a method of adding capacitors to an electrical system to compensate for inductive characteristics of some loads. Capacitors are connected to the load, providing reactive power against inductive loads. This method is effective for improving power factor in lagging loads commonly found in industrial application. Inductive compensator, also known as synchronous condensers or inductive reactors, is used to increase power factor in systems with excessive capacitive loads. Combination correctors is a system that combines capacitive and inductive compensation techniques in a single system, used in situations where power factor fluctuates depending on the load it uses. It uses a combination of reactors and capacitors to maintain the required power factor, making it suitable for complex and dynamic electrical systems. Control strategies. Automatic power factor corrector systems are various control algorithms to optimize power factor. The systems offer advantages such as improved energy efficiency, reduced voltage drops, and precise data gathering. However, they may not be able to correct power factor due to limited correction range. Real-time monitoring provides precise data, but can only costly due to the need for sensors and data collection equipment. Adaptive control offers durable performance and improved energy efficiency, but may be complex. Feedback control voltage regulates voltage, improving equipment reliability and power quality. However, it may not directly optimize power factor optimization. Harmonic filtering reduces harmonic distortion and improves power factor quality, but may be more expensive and require filter replacement and maintenance. Control current improves current regulations, shields equipment against overloading, but may not be the main technique for optimizing power factor. Automatic power factor systems is crucial for efficient electrical systems operation and maintenance. It consists of several components including capacitor banks, central controllers, measuring devices like CTs and VTs, switching devices like contactors and thyristor switches, protection devices like overcurrent, overvoltage and undervoltage protection, HMI operator monitoring and communication interfaces between integrated of SCADA systems for remote control. These components work together to maximize reactive power compensation and improve power factor. Challenges and limitations associated with an automatic power factor systems as identified in the literature review. Overcorrection and overcompensation, capacitor bank sizing and configuration, transit loads conditions, harmonics and resonance, maintenance and aging, operational costs. Methodological approaches, literature review, data collection, simulation studies, data analysis and statistically of methods, surveys and questionnaires, cost benefits analysis. This brings us to the conclusion of our literature review. The analysis of the literature of an automatic power factor correction system offered a thorough overview of the essential aspects of electrical engineering and energy management. We have looked at the essential components, control methods, challenges, benefits, limitations, recent trends in automatic power factor corrector throughout the review. It is obvious that an automatic power factor systems serves a critical role in improving energy efficiency, decreasing energy losses, and ensuring the reliability of an electrical system. This is a decision matrix that was used when choosing the best option, of which the option that was chosen was buying some of the material and building some of the material. These are the subsystems. This is a figure that indicates or that explains the subsystems that was involved or that was used when designing the report, of which it's going to be explained in the following slide. The Arduino automatic power factor correction systems uses a potential transformer and current transformer to step down voltage and current, which are then fed to a zero crossing detector circuit. The output of the zero crossing detector is a square wave representing a zero crossing of AC waveform. Two separate ZCD circuits are used for voltage and current waveform, and the output is summed using an exclusive OR gate. The phase angle is then given to the Arduino microcontroller through pin 10. The selection of component values. This is a list of all the components that is going to be used during the building of the project. These components, they range from our Arduino board, power supply, our LCD screen, our XOR gate, resistors, breadboard diodes, amplifiers, the choke as our inductive load, our incandescent bulb as our resistor load, USB cable for our Arduino, connector wires, capacitors, potentiometer, as well as an amplifier LM324. These are the simulation that was done during the report. So the software that was used was Multisim. This is a continuous slide of the simulation that was done on Multisim. The compliant tests. Test setups including a step-by-step approach for ensuring that the intended solution fits the user requirements. This project seeks to design a system that will automatically regulate the power factor of an installation. In this project, we will only build the prototype version of the electrical installation to be regulated in our circuit. We will have a number of resistors and inductors connected in series. As well, we all know components with high inductive material are most significant contributors to worsening condition of a power factor. And connecting capacitors in parallel is one of the most significant contributors. Our prototype circuit is designed with this in mind. The steps below will walk you through the process of testing of our circuit. Connecting a sequence of resistors and inductors, connecting an alternating current supply, gradually rising the inductive while keeping an eye on the power factor, connecting the capacitor bank one by one while monitoring the power improvement on the watt meter, increasing the capacitor value until the power factor reaches unity. The cost analysis of all the components that was involved or that will be involved in the building of the prototype. The Arduino Uno board will cost 320 rands, the power supply 74 rands, the LCD screen 139 rand 20, the XOR gate 18 rand 33 cents, with the resistors 30 rand, the breadboard 119 rand, the diode 60 rand, the choke, which is the inductive load 84 rand 95, and incandescent bulb 60 watts, which is the resistive load, will cost 60 rand. The USB cable connector for Arduino will cost 20 rand 72. Connecting wires, we're going to use recycled connecting wires. Capacitors 30 rand, potentiometer 10 kA 20 rand, the LM324 90 rand. Concluding, this work addresses low power factor corrector issued by designing and modeling an automatic power factor corrector. This device increases the efficiency of active power transmission, saving cost, shortening development times, increasing power supply and data rate. The device improved the power factor from 0.76 to 0.97 under test load condition, resulting in a significant energy consumption saving. Future work should focus on real-time operating in mine substations, avoiding harmonic problems caused by frequent capacitor bank switching, and determining the ideal location for correcting equipment for maximum utilization and saving. We've come to the end of our report presentation. I'd like to give special thanks to the professor that guided me through the research process, the writing of the report, and thank you for listening.